In this question, we're calculating the greenhouse effect, the process by which a planet's atmosphere holds in heat, allowing the planet to have a much warmer surface temperature than you would expect from sunlight alone. Since the process depends on the atmosphere, it will also give us a direct indication of how much atmosphere the planet has. Note that in this question, we're just looking at the inner planets. The thick atmospheres of the outer planets also produce greenhouse warming, but it's more of a challenge to define a no greenhouse temperature to compare against on these worlds, since most of them don't have solid surfaces. The greenhouse effect is an atmospheric process. Sunlight is absorbed by a planet's surface and is then re-emitted as infrared light. However, greenhouse gases in the atmosphere trap this infrared light, making the surface and lower atmosphere hotter. So the result of this calculation will be a measure of how much warmer the surface is than it would be if the planet had no atmosphere. This will also tell us how much atmosphere the planet has. There are just a few pieces of data that the question gives. These are the measurements of greenhouse warming on Venus, Earth, and Mars. Since you will want them for comparison, you should write these values down here. Greenhouse warming depends mostly on the presence of an atmosphere. The thicker the planet's atmosphere, the more greenhouse warming it's likely to have. For terrestrial planets, forming an atmosphere depends on being large enough to be geologically active. So you wouldn't expect much of an atmosphere on worlds that are too small to have mantle convection. Beyond that, a number of different processes can impact how thick the planet's atmosphere will be. So while it's possible that the biggest inner planet will have the most atmosphere, it's not guaranteed. For example, in our solar system, Venus has a much thicker atmosphere than Earth, even though the planet is slightly smaller than Earth. Nonetheless, if you want to simply predict that the largest planet has the most atmosphere, that would be reasonable here. If you'd like to take a more mathematical approach, one thing you could do is look for odd effects in the wavelengths of light emitted. Remember that cooler planets emit longer wavelengths of light. So if you find a planet with a low no greenhouse temperature, but which is also emitting relatively short wavelengths of light, that would be a candidate for a planet with a lot of greenhouse warming. There are two equations in this problem, one that we've already used before and one that's new. The one we've used before is Wien's law. That's the equation we used earlier to calculate the temperatures of the outer planets. In this problem, we'll start out by doing exactly the same thing with inner planets. The second equation simply defines how much greenhouse warming a planet has. The amount of greenhouse warming is just the difference between the actual surface temperature, which you calculated from Wien's law, and the predicted surface temperature from solar heating alone. This is also known as the no greenhouse temperature. So there are two sets of numbers we need to look up from the Mystery Solar System table. The first is the wavelength of light emitted, and the second is the no greenhouse temperature. List those values for all three of the planets you're calculating, including the one you picked in your prediction. Just as with the surface temperature calculation earlier in the term, we don't need to do a unit conversion here, so you can leave that box blank. This part works very much the same as it did when we calculated the temperatures earlier in the semester. In this case, let's assume a planet that is emitting light with a wavelength of 7,000 nanometers. We plug this value into the Wien's law equation and simply divide the constant by the wavelength to get the surface temperature in Kelvin. Remember that room temperature is around 300 Kelvin, so clearly this planet has a much hotter surface than the Earth. To find the greenhouse warming, we simply subtract the actual surface temperature from the no greenhouse temperature. In effect, we're asking how much is the atmosphere making the planet's surface hotter than it would be otherwise. Let's assume that the no greenhouse temperature is 290 Kelvin. If we subtract this from the actual surface temperature, we get 124 Kelvin. Remember that 124 Kelvin isn't the temperature on the surface of this planet. It's how much the atmosphere is making the planet hotter. So this leads us to part D of this question on the implications. If we compare this much greenhouse warming to planets in our solar system, we see that this planet has 3 times as much greenhouse warming as the Earth, but far less than Venus has. This suggests that the planet's atmosphere has significantly more greenhouse gases than the Earth has. This could be because it has a much thicker atmosphere, or just that greenhouse gases make up a larger part of its atmosphere. Remember that greenhouse gases are only a small fraction of the Earth's atmosphere. So it would be reasonable to say this planet's atmosphere is as dense or denser than the Earth's. Now it's time to check that your answers make sense and are consistent with your predictions. Remember that if the result turned out different from your predictions, it's okay to talk about that here. There are many factors that go into determining how thick a planet's atmosphere is, and not all of them will be obvious just from looking at the Mystery Solar System table. You should also look at the values you get for the actual surface temperature of the planet and decide if these make sense. Since these are inner planets, none of them should be as cold as we saw in the outer solar system. Anything much below 200 Kelvin would be very surprising for an inner solar system planet. On the other hand, temperatures much above 1000 Kelvin would also be very unlikely on a planetary surface. At that temperature, the surface is probably molten rock. So if you're getting a surface temperature that is well outside of that 200 to 1000 Kelvin range, you should go back and check your calculations. Also, the amount of greenhouse warming shouldn't be negative. It's possible for the greenhouse warming to get down to -1 Kelvin because of rounding errors, but much below that suggests a problem with the calculations. So say whether or not the results match up here. If you're not sure, feel free to ask for help.